Hi everyone. So today, this lecture, we're going to wrap up the integrator, the pulse integrator that we didn't get to cover um, in lecture 5B, which is the last section in 7.4. But the main course of this video is going to be on instrumentation amplifiers, and this is actually what most people use, well, at least most physicists use, because a lot of times we don't want to try to design it's an amplifier that's very simple to use and has all these noise reduction and common mode rejection ratio that are very large, so therefore we don't have to worry about it. And typically that's what we buy, so we spend an extra $10 on something, and then you don't have to spend an hour, well, maybe 10 hours designing it. But let's wrap up the integrator, which is the amplifier we talked about last time. And this is known as a pulse integrator, and then you're going to see why this is going to be very useful in a lot of experiments. The reason it's called pulse integrator is because whenever a lot of instruments, the signal that comes out doesn't come out as sine waves or cosine waves. It comes out as pulses, so you just get this one jump and then goes back down. So draw that. Okay, so let's say you have some signal that's a function of time. Oops, let's draw a straight line, straighter line at least, right? And then you're waiting for a long time, and the pulse, let's draw that in red, comes out like this, and then decays like this. Okay. And typically, the thing you care about, so with volts, it's function of time, right? The thing you care about is actually the area under this graph, okay? And you can see how a integrator, right, will do that for you, right? To compute this pulse area for you, right? And typically, these pulse areas are going to be proportional to maybe the amount of energy that was deposited into a detector, or how much light comes out of a laser, right? So the number of photons, right? And that's very useful for physics analysis, okay? And you can make this with your integrator without all the little frills. So all you have to do is basically do your integrator circuit, and the modification you do is you basically set a gate on it so that it can get reset. Because what happens is that if you just integrate over and over again, right, the charges, the pulse area just keeps adding up. So what you want to do is be able to reset this. The way this reset works is through a MOSFET. I know I didn't cover this in the lecture, but the basic functionality on a MOSFET in this case is really literally just a switch. Okay, the way the switch works is that if let's do the integrate part. Okay, if the voltage at this reset latch, right, is at -15, what happened is that the switch, you can almost tell, right, the wire connects here. This is known as the gate. Okay, this is known as the source, and this is known as the drain. Okay, so the gate acts as like the base compared to BJTs. The source acts as the collector, the drain acts as a emitter. So hopefully those words have some connection to each other. But what happened is that the difference is that when the gate is at -15 volts, right, this circuit is open, right? The source to drain is open. Let's just say that source to drain is open, right? Okay. But when you switch it on to 15 volts, what happened is that then the source and drains are basically connected. Okay, to drain, it's basically a transistor switch. Okay? So how that works is that, right, you have some pulse that comes in, you have some resistors there that generate some current. This is a very fast signal, so most of that will actually go through this capacitor. Therefore, you get an integration just as you expect. But what happens, what happens that, right, now, go down, okay, now, right, you want to reset and basically drain all the charges of this capacitor. So you close this, and what happens is that you basically connected the two sides of the capacitor to a wire, and all the charges just go away. Okay, and this is known as a pulse integrator. And that way, you can have the integrator ready to integrate, or you can reset it. That way, you can reset the pulse area that you're measuring. Right. So that's sort of the last piece of some of the circuits that we dealt with last section. Just the high pass and low pass filter, also known as a integrator and a differentiator. Okay, so the next thing we're going to talk about are instrumentation amplifiers. These are what most people will use in physics because we're not, we don't want to spend the time designing and basically finding all the resistor matching and all the transistor matching. This is what actually you'll mostly see in a lot of consumer devices because they're just cheap. Well, they're more expensive than op amp, so an op amp would be like, you know, $1 to $2. Where an instrumentational amplifier of the same quality is probably going to be closer to $10. But you're going to see that this is actually going to be like 3 op amps together. Okay, and let's see this. Okay, so to kind of motivate this, the differential amplifier, the ones we studied before, what it has, right, it has 2 inputs, a negative and a positive input, and these resistors are matched together, right, and then R2 are also matched together so that both the negative and the positive side has the same gain. Okay, because what happens if they have different gain, then is the one side's going to pull it very negative, or one side's going to pull it very positive. Okay, so, and another problem with just having just these differential amplifier, let's label this just a differential amplifier, because this is not an instrumentation amplifier yet, that the input impedance tends to be fairly low, because if you look at the positive side, right, so the route to ground is through this R1 and R2, so, you know, R2 could be pretty substantial, right? But it's not like where we had the transistor amplifier, where the path to ground actually has to go through the transistor, and therefore it actually has a very high input impedance. Where in this case, you're just routing it outside the op amp, so therefore you don't get that effect of beta. Okay, it's even worse on the negative input side, because, right, this point here is acting as a virtual ground, right? Right, the virtual ground here, right? So what's happening is that Cn is basically R1, and that's it. And you can pick R2 to be very large, but R1 has to be very small compared to R2, because your application is basically the ratio between R2 and R1. Okay, so and this also goes to a thing that's going to be important, which is the thing we'll discuss in the transistor version of this common mode rejection ratio, right? In order for this to be, the book gave an example. If you want this ratio to be about 10 to the 4, or about 80 decibel, you need resistor tolerance that are within 0.01% of each other. So these resistor has to match with each other within 1 in 10,000. So if you have a 10k ohm resistor, right, they have to be within 1 ohm. So it's plus or minus 1 ohm, which we don't have, right? And especially in the labs we're doing this in, right? These resistors or tolerance are like 5 to 10%. You can buy better ones. You know, as you buy better ones, they can get more and more expensive. Okay. The way we fix this is by adding a unity gain follower buffer to the input. Okay. I think I'm going to have a different version of this. And this is known as the classic instrumentation amplifier. Okay. So you have your differential amplifier here on the right? These two resistors, right? In this case, you basically make these R values the same, okay? And we're going to see how that's going to be used in along with the left-hand side here, which are two different, okay, unit gain amplifier, well, unit gain op amps. They don't actually amplify a signal. So, because remember, when you just connect the output directly to the negative input, you only get a unity. You get a gain of 1. So let's see how this circuit actually works, right? So let's analyze this part here first. I'm going to highlight that in red, right? Because this part is the only part that's we're really adding. The stuff on the right is just a differential amplifier that we already have the equation for from up there, right? So, okay, I'm going to assume that the current, well, the assumption, I'm going to assume that the input is on the positive swing, because remember these differential signal, right? Your V plus, right? Let's say this is V plus, right? Can swing up and down like this. The V minus, right? Since we're trying to amplify differences, right? Can swing in the opposite shift, right? So V plus and V minus, they're just labels, okay? So V plus doesn't mean it's always going to be positive. V minus doesn't mean it's always negative. They're just relative to each other, right? And it's the difference that you're going to be amplifying between them, okay? All right. So, what's going to do? Oh, and one thing I also want to mention is this R1 here is usually an external resistor. I'm going to see how that's going to be useful, because that's going to allow us to actually adjust the gain of this instrumentation amplifier by only swapping that one resistor without having to deal with any other components in there, okay? All right. So let's examine what's happening here on this left-hand side here with this 3 resistor chain, right? That's connected to the output here. I'm going to erase the color so we can actually label them previously, just to clarify what's going on here, okay? Because this is, I'm going to call this V out plus. I'm going to call this V out minus, okay? And this here is going to be V in minus, okay? And this is going to be V in plus. Let's say that. Okay. Let's not label this actually. There's actually no point in doing that. Okay. So if we look at this little resistor chain, right? This this top part is connected to R2, and then it goes to basically, okay. The reason I'm not going to label them, right? This is the negative input, the inverting input of the operational amplifier that's going to take the negative differential input, okay? So what happened is that this, right, one of the rules of op-amp is that the op-amp is going to try to make the inverting and non-inverting input to be the same voltage. So therefore, right, the op-amp is going to try to make this V minus. That's why I didn't want to have a separate label for them, okay? So therefore, we can label this point between R1 and R2 to be V minus. Similarly, I can get out of this, right? The V plus inverting input, right? The op-amp over here is also going to try to make this V plus, okay, not V in plus, okay, be a little careful, right? And that point is connected between the R1 and the second R2 resistor, okay, and these are going to be matched together, okay, all right. And then of course the bottom of this resistor chain is going to be connected to R2, okay. And the reason we can do this is that, right, the idea is that the whatever current goes out of here, right, that's going to go through this feedback loop, okay. We're going to see how that's going to give us a differential amplifier, okay. So what we're going to do is follow rule number 2, right? The voltage between the resistors can be determined. Oh, I'm going to read up here, okay. And I'm going to assume that the signal, the V plus, is on the positive swing, so therefore the V minus is on a negative swing. And what happened is that since this is going to be higher potential versus here, what's going to happen is that the current is going to flow this way. Oops, sorry. The potential at V plus is going to be higher at V minus. I'm going to then assume the current is going to flow that way. Even if you assume the other way, the current will just flow in the opposite direction, and then all the signs will flip, and then the same thing will happen. Okay. Then what you can do is use rule number 2, right, to figure out the voltage between these resistors. Okay, so what we're going to do here, see, let's do V out plus first. Okay. Well, actually, let's not do that first. Let's do the calculate what this current is in terms of this resistor value and V plus over V minus. Because all we have to do is use Ohm's law, right? So the change in voltage, right, which is V plus minus V minus, be a little careful with these signs here, right? It's going to be R1 times whatever this current is. And the reason you don't have to label this is because since this is going to be a single current, using rule number 1, so that these inputs don't actually draw any current, so you only have a single current flowing from V out all the way to V out, sorry, from V out plus all the way to V out minus. Okay. All right, so solving this for I, you're going to get equation 7.30. Okay. Now what we can do is that, well, we know what the current is, so therefore we can actually solve for the rest of the voltages. Okay. So V out plus, which is what's on the bottom here, right, minus the current times R2, which is this voltage drop, is going to get you to V plus. So that's the equation I'm going to write down here, right? What we can do is substitute what I is. Okay, if you substitute in what I is, we end up with that V out plus, right? It's going to be equal to V plus times this ratio of R2 over R1 times the difference between the two differential inputs. Okay. Similarly, if you do the Ohm's law analysis, basically, right, from V minus, right, V minus minus I times R2 gets you to V out, right? So V minus minus the voltage drop across resistor 2 gets you to whatever V out minus is. Okay, right? Once again, replacing this I with what we found up here, right? Put a little star there, right? Right? You're going to find that V out minus is going to be V minus minus R2 over R1, same ratio, times V1 minus V. Sorry, V plus minus V V plus minus V minus. Okay. A lot easier to read than to say it. Okay, so for a differential amplifier, basically it should amplify the difference between these two outputs from your first stage, right? So these are the outputs from your first stage. Control Z that, right? Right. These actually goes as inputs to your differential amplifier, right? So the difference between these two guys, right, is going to be amplified. Okay, so therefore, if you just take V out plus up here, subtracted to V out minus. Let's write these, let's circle these. Right? This is V out plus. This is actually V out minus. You subtract these two things, okay? What happened is that then you still end up with a factor of V plus, V minus, right? But since there's a sign switch between them, the minus of the minus gives you a plus. You get two factors of, two times R2 over R1 plus the times the difference between the two inputs. Okay, you can do a little factoring and factor this V plus minus V plus minus V minus, right? You end up with the gain of this instrumentation amplifier as 1 plus 2 times R2 divided by R1. And that's going to be very useful. Okay, and so notice that the instrumentation amplifier, right, go up all the way up here, right, these resistors in here are all internal to the integrated circuit. Okay, so the manufacturer is going to match those resistance, so you don't have to randomly find two different resistors in your bin, and hopefully they are close to each other. Okay, these are made in order to have these resistance match to them, and the only thing you need to do is actually plug in an external R1 resistor, right? Because if you change what R1 is, you change the gain, right? Notice that if you completely remove R1, which makes it makes the resistance in that wire infinite, right? If you remove a resistor, you basically have an open circuit, right? The gain will just become 1. Okay, it doesn't go to infinity or something like that. Okay, right. You can find these instrumentation amplifier starting with part number INA. Hopefully that makes sense. Okay, and you can actually find this. The ones that the book mentions, the INA 128. This is the 120 INA 12X. The X just means, oh, you know, it could be any generation. It could be INA 120, 21, 23, 24, right, and so on like that. Okay, and this is a precise and low power amplifier. Okay, some of the specification you're going to see here is that there's, you know, some low offset voltage, some small bias voltage. The thing that you want to think about up to this point, okay, is this high CMR. The common mode rejection is 120 decibel. Okay, so 120 decibel, what is that equal to? Right, so if you divide that by 20 decibel, that's equal to, and you take that to 10, right? Because you're basically converting the decibel scale to just regular scale. So this will give you what, 6? So yeah, 10 to 6. So you have a common mode rejection of 1 million between the common mode versus the differential mode. Okay. Let's see, is there something else we can look at here? Electrostatic. So there's also, you know, electrical characteristics, right? So this common mode rejection ratio, right? If you put in the gain of 1,000 in there, you get a minimum common mode rejection 120 decibel, which is pretty good. Notice that if you put in a smaller gain, right? Put in a smaller gain here, you get 120 still, but when your gain is pretty small, your common mode rejection actually gets smaller, right? Because one reason is that the common mode and the differential mode may not scale the same way, where the differential mode scales down a little bit quicker as you reduce the gain compared to the common mode. Okay, and then so if you go to gain of 1, which is not amplifying at all, then you just get common mode rejection ratio of 80, which is 10 to the 4. Okay. There's other interesting specification here. So these are similar to what we have. What you want is If you have a dual supply voltage plus or minus 15 volts, it's probably what you want to run it at. Other interesting things. Okay, but you're gonna see this. You can see this by just looking for, once again, searching on internet for INA128 datasheet, and you want to grab the one that has it from a company that you can recognize. And in this case, once again, Texas Instrument. Typically, if you don't recognize the name, it's still okay, but sometimes they make them slightly different from each other. Okay. So I'm going to spend the last couple of minutes just so that I can talk about some of the application, meaning what these instrumentation amplifier can be used for. One of them is a thermocouple amplifier. So what a thermocouple is, I don't know, is a thermometer. The cool thing, so one of the things we learn about, right, when you have a PN junction, right, that this depletion zone, right, is actually gonna, how much the amount of current flowing through this actually depends on the temperature. Okay. The way you make this is not with the p-doped and n-doped material, but just two different types of metal. Usually it's something pretty heavy, like copper versus tin or something like that. And due to the fact that there is there are different material, what happened is that some of the electrons will migrate from one of the material to the other. Okay, so this is conductor as opposed to semiconductor. So all of the, let's say the tin is the one that's donating the electrons, so the copper gets all this. Right now you have a slightly positive here, so now you just have a delta V between these two things. But these delta V is going to be very, very small, something on the order of nanovolt to a microvolt. So what you want to do is to amplify this. Okay, and the way you do this is basically by connecting these to the differential input for a instrumentation amplifier. In this case, I guess they set the gain to 100 for whatever reason, and then you can use this, right? Whatever, yeah. So sorry, RG is that R1 that we have in the derivation, right? That RG is basically the same as this R1 here, which is what sets the gain of your instrumentation amplifier. I should mention what R2 is in this particular amplifier. Yeah, so R2 is 50 kilo ohm. Okay, so in this case, if you want the gain to be 100, if R2 is equal to 50 kilo ohm, you want this to be 100, so you want this 100 times smaller, so 500 ohm, right? So you put in RG equals to 500 ohm, you get a gain of 100. Okay. And then you get the V out, so this will be 100 times whatever this small delta V is, right? And therefore you can actually look at the voltage across it. This is how a lot of temperature are measured inside devices such as my phone. My phone has a little well, maybe not just one, maybe 3 or 4 temperature sensor in it, just so that, if let's say the CPU heats up too much, right, it can shut itself off to protect itself. Okay. There are also differential transmission for noise rejection. So if you use a cable modem, for example, what happened is that you're sending the signal from the cable company, right, and it goes through some coaxial connection, right, some cable. On the receiver end, you may see a lot of common mode noise, meaning there's some 60 hertz noise from running through the wall, so they both kind of go up and down at 60 hertz, but then there's additional signal in between them. So you can use an instrumentation amplifier, right, and you can set this RG to be whatever you need in order to get the gain that you want. If you remove that, you would get a gain of 1, remember? Okay, and what you do is you add this along with an RC here, right? Which kind of takes out some of the ground noise. So the outer shell here is typically the ground signal. The inner core is actually the incoming signal itself. So what happens is then you're amplifying this output so that your television will have the sufficient signal that's been amplified in order for it to detect the relay the information that it needs. Oh, your cable modem, and we're going to talk about modems in the future pretty quickly. Okay, so these are some of the applications that you'll see with differential instrumentation amplifiers, and these are typically the ones we actually use in a lot of cases because we don't want to go into the nitty-gritty of matching the resistor values of stuff like that. Okay, all right, so that's 30 minutes. So hopefully then, so that's all we're going to cover for this module. We're going to continue on this module, continue on the same chapter next module for more study of operational amplifiers, because these are actually the ones that most physicists would use most of the time, and a lot of hobbyists use them because they're easy to use and they're designed so that you can just pop a chip on something, change one resistor, and have a gain that you want. Okay.